Hello there. Welcome to another concept section, and this is a little bit advanced. I would say a little advanced in our treatment today. So if you're really a beginning student, probably you won't get much from this, but you might get some from this. So just bear with me and watch it. So what are you going to use to actually address this? We're going to use complex algebra, and in complex algebra we're going to rely on a thing called e to the power I theta. It's called Euler relation. Is cosine theta plus I sine theta, and you know I equals to square root of -1. If you have the expression like this, then it's complex algebra. So this is the real part, it's called real part, and this is called imaginary part. So if you write something like E is the Euler constant, E to the power I theta, so this is very important. So if any other real number, a plus ib, can also be written as some a e to the power I theta, and this a will be square root of a square plus b square. This is called amplitude, magnitude, let's call it magnitude. And this theta, when you write in this form, theta is called phase, and this number is some complex number, say z. Another way these complex numbers can represent it is so if I here do real and this is the imaginary part, then these are real numbers, so real part, imaginary parts. So if I call this guy x and this guy y as variable, so this will be like x, the real part of z, imaginary part is z, so this is y, and so this number here is a and b, and this is a plus ib. Okay, I know my pen started to not work anymore. Okay, so you can see that from here to here, that distance is this magnitude a, and this angle is that theta. And you can, from here you can also say a equals to a cosine theta. Like over here you could have expanded this guy using that, and you come to conclude the real part of this equal to real part of that, and b equals to a sine theta. So in complex algebra is another thing that happens if you have some expression, say z1 equal to something z2. So this one has a real part a1 plus ib1, this one is say a2 plus ib2, and these guys are real, these are real, so a is b is real. Then this kind of equation says real part of this must be equal to real part of that. So real part of z1 equals to real part of z2, and real part of imaginary part of z1 equals imaginary part of z2. This is where the power comes in algebra. When you're doing algebra, lots of algebra you can do, and then eventually you can get something where you're looking for just the real part or just the imaginary part. So in the wave, the use of complex algebra comes from suppose wave is cosine, not just waves, in like oscillation. So just oscillation is a cosine omega t, and some amplitude and some phase. So this will be like a harmonic oscillator, this up and down. This could be a solution of harmonic oscillator. So everything is real, omega t, everything is real, all real. So if you're trying to do a whole bunch of harmonic oscillations, adding and subtracting them, sometimes adding cosines and sines is a very big problem. So you can represent this as a real part, because this cosine a e to the power I omega t plus phi. So if you have a real part of this, sometimes people use a curly bracket just to emphasize that this whole thing is not the answer. This thing, so this actually is equality. Further, sometimes e to I omega t may be common in all calculations, so it's going to be nice to just do separate out this and e to the power omega t. Sometimes it's the same thing as that, but this, then you say, well, this is the one that's varying, but this is constant, so this now is an amplitude, and we can call this a new amplitude, and we usually use the tilde to denote the complex. So this is complex. So this A is a real amplitude, and sometimes we're going to call this a complex amplitude. Of course, in the end, we have to, whatever we do, sometimes we just work with this, and this remains a silent partner till the very end, and then we put it together and the calculation proceeds. So this is the kind of calculations we do using complex numbers. So in the wave, you'll have a very similar thing. In the wave, you'll have a cosine kz minus omega t plus phi. Could be electric wave, magnetic wave. So here is a xz plane, xy plane, and the wave is going this way. So this could be a wave going in that direction. So this wave, you can say, well, I can, if I'm going to use a complex thing for analysis purposes, then I'm going to write this as a real part of a e to I kz minus omega t plus phi. And just like over here, I can separate these out, things which depend on variables like z and t, z and t, and this is just a constant, so I can absorb it into redefine amplitude. So a e to the power I phi, and so this is a complex amplitude e to the power I kz minus omega t. So this will be same in all the waves, and this may be the thing of concern. And turns out, when we deal with the polarization of waves, this is an important thing to separate this out and just talk about this complex part. But you have to put it back together, and so that's your actual wave. So this is real and this is complex, and this stands for this whole thing. Okay, now let's do our ENM, just a little bit of a review of how we're going to do complex numbers. Okay, so the example we're going to take is, example will be a wave is traveling along the z direction. So this is the direction a wave is traveling. Okay, and so you can see that if the wave is traveling on the z-axis, electric field in any of the planes can be pointed in the xy plane. So electric field, so this wave direction, and this is the direction for so-called k vector, wave number vector. Like k here will be some value k and z hat, and the frequency, angular frequency will be omega. So that will be, we're going to denote the notation. So E at any, we're going to say, we're taking a plane wave. So E at any point, like any arbitrary place, you know, x, y, z, t will be only dependent on z and t. So if I go in this plane, it's going to be same everywhere. At this point, it's going to be same. At this point, same. So if this electric field is the same at all of these points, and it's going to have some x component or some y component. You can see from this notation. So you can have some x hat. It's going to have its own amplitude and have a cosine kz minus omega t plus its own phase constant. So this is along the x component. Y component can have its own wave. So it's kind of like this is the wave which is going parallel to x-axis, and this is the wave is going to parallel to y-axis. But they're independent wave. So these are parallel to wave parallel to x-axis and wave parallel to y-axis, but they are independent. They are independent. So like, this is not a function of that, this is not a function of that. They're not related to each other. When you have two waves, you can set one of the phase to 0 as a reference, but you can't set both of them to 0 unless they are actually in sync. So they can be completely out of sync. Okay, so you can see I can do this as long as I do this. Addition is a linear, so I can do this like a real part of x hat e0x e to the power phi x plus y hat e0y e to the power I phi y e to the I kz minus omega t. So this will be common to so because this is addition, which is a linear operation, it will just come out, it will be exactly that value. This will be that value. Make sure you understand those. Okay, make sure that you got that. Okay, so because this part is the common to all of the calculation, we can just kind of set this part aside and do calculation with just this part. Just calculation with this part. And you can see this is a complex, it's kind of it's strange. It's regular vector, but its components are complex. So we need a notation. Let's call it some kind of script e0x. This is a complex. And e0x is real. This is real. This is real. And this one can similarly say e0y. Just so the notation can be, and this whole thing we can just say e0 vector. So e0 vector is this complex now. I can write x hat e0x plus y hat e0y. And you may remember the vectors you can write like this in the xy, or you can say this, I can denote it, it will be same way, just the components as a column vector e0x e0y. And so this is a column vector. So this is because this gives a electric field and everything. You can the direction of this vector is what is called polarization. So this is a you can say here that this is kind of a strange so-called direction is polarization direction. So wherever this vector is pointed, so it's going to be, this guy is pointing that. So because I put it there, but here it's a physical, so this actual direction E is polarization. But here it's come in the code because these guys are complex, and how you're going to plot it, you can't plot it. Okay, so you can only discuss this formally. All right. Okay, so what are some of the examples? Let's look at the examples. So say you have a let's look at a x, y, x, y. Normally this is a good notation rather than write all of that. You mean this, but you write like that. So so let's look at one example. Suppose wave was going back and forth only along the x-axis. So this vector will be 1, 0. We reprint this as 1, 0. Of course, if there is something multiplying there, let's call this E0 multiplying there when you write this thing. That means here what we have is a phi, and so e to the power I phi x equals to phi y equals to phi, and ex equal to E0, ey equal to 0. So that whole thing can be represented like this, and we kind of omit this. So this is omit in terms of writing, is understood. We just understand that it's there, and when we're putting it back into this thing, we have to put that back. But this is the case. So this is the x polarized wave. Okay, and similarly, y polarized wave would be, you'll have an E0 e to the I phi, this kind of, and then 0 and 1. This will be y polarized wave. So just don't worry about that. This is going to be y polarized wave. And you can see that this is a unit vector, this is unit vector. So usually notation is to just extract the most fundamental information that's contained in the polarization information, and that's the direction of the field, direction of the electric field. The net direction of this electric field is contained in this. Okay, what's contained when you put them together is, now we have two waves. They may be in phase or out of phase, right? So these guys are actually only one wave, the other wave is 0. So when you have two waves, they can be in phase or out of phase. Let me erase and see if I can get more space. Okay, let's do the other cases. So suppose, what if phi x is not equal to phi y, but phi y is actually phi differs by, say, pi over 2 radian. So they're all real, right? So there's no imaginary here. And ex is ey, and let's call it a. Okay, so what will we get? We will get a e to the I phi x, b e to the power, a e to the I phi x plus I pi over 2. Taking common factor out is a e to the power I phi x, and you have a 1 e to the I pi over 2. And this is left circularly polarized wave. This corresponds to, in a previous lecture, we know that this will correspond to 1 is called I. So this is a counterclockwise clockwise rotating field. So if I look from in the xy planes, this x, y, and z is coming out, then electric field in say at z equal to z1 is that way, at z equal to z1, and a little bit later is that way, a little bit that way, a little bit that way. It actually rotates and as the same magnitude, so it rotates counterclockwise. So this is also called left circularly polarized. Okay, and it's also called, because the positive is called positive helicity. So this is called helicity positive. Now, you wanted to know what the field will be, what would you do? And I've been alluding to the fact that you have to go back, take this, and plug in here to get that. So let's see. So 3 will look like this, okay? So you will say, okay, my electric field x, y, z, t is real part of x hat. I mean, this thing is all common, so it's x hat and plus e to the power I pi over 2 y hat. So that's the common part. The rest of the common part, that's going to be a e to the power I phi x, which is arbitrary, and then this whole thing. So this whole thing is coming from this part here into that. This is E0 complex, and then e to the power I k z minus omega t. So this, when you work it out, the real part of this will be just that, and the real part of that will have to be include this in there, and so it's going to be x hat a cosine kz minus omega t plus phi x, no surprise there, plus y hat will be actually y hat will be cosine this whole thing, let's call this theta, but then I have to add pi over 2 over there. So this will turn out to be negative y hat sine theta part, the theta part. So that's how you can when theta is 0, when this thing is 0, is pointed along the x-axis. When theta is pi over 2, is pointed along this axis. So theta is 0. Yeah, so it's actually going this way. Just wait a minute. So there is a little problem here. I just discovered. No, it's not going this way. It's going this way. So this is at z equal to 0. So z equal to 0. So you cancel that, and then this becomes minus omega t. So when minus omega t, you bring this outside. So this becomes minus omega t plus pi over 2. So when you pull minus out, this remains plus. So this remains plus. When you pull the minus out, then becomes, this is minus. And so this becomes a plus. And sine minus pi over 2. Oh, this plus pi over 2. Sine plus pi over 2 will point over there. So let me clean this up, because this got too much problem here. Okay, so because of space, I just got a little bit too many things down there. So let's redo this case. So starting from this, I can plug in there and get the real part like this. So real part of the x hat and real part of the y hat, they're off by pi over 2. This angle is theta and this angle is theta. So if I use the cosine a plus b, I can get so this is theta. I get a minus sign here, and this is theta. Now let's look at z equal to 0 just for the drawing purposes. So you're going to get something like this, and pick this also just for drawing because it's arbitrary and shouldn't make a difference in the behavior. So you will see this counterclockwise rotation, and so this is a counterclockwise rotating E field, and this is happening in time, but this same thing happening in space. So if this is the z direction, you will see that as the electric field, so electric field is pointed always in this plane. So but if you look at from here and project all of this on here, then you're going to get, it's going to be going this way when you're looking down from this side. Okay, so that's a circularly polarized. So there would be another variety of this when this is minus. So this is like could be plus or minus. So this could be plus or minus. So plus thing we'll discuss. Then you'll handle with plus and minus here. So you can just use this as a indicator of polarization. Okay. And we come down here, so plus or minus. So this is going to be minus or plus, and then you'll end up with plus or minus. With a minus is, so when you have a minus, it actually rotates this way. So if you start from this vector, the next vector will be this vector, this vector, this vector, and this will be, so it's a right circularly polarized. I think that's what it will be. It's going like a right-handed screw. Okay. So what's the elliptic polarization? Is a generalization of this, in which so these are 3 and 4 cases. It will be the elliptic polarization will be, then like we have a E0x, E0y, maybe phi x can be arbitrary, phi y, they're not they're completely independent, and that's the most general case. Okay. So there are 2 kinds of most general case. One is, we can say these are arbitrary, but then these guys are off by pi over 2, kind of like over here, but here they were the same. So we can relax this. So they don't have to be same. One can be A, another can be B, and let's see if we can look at that case. Okay, so in this case, let's look at this vector, the E0 vector. So complex vector is, I have A here and e to the power I phi x, and I have a B here, e to I phi x, e to I pi over 2. And let's see B over A, let's call it B over A, is some relative size difference. So I can pull one out. I can pull, so this will become 1, and then so e to the power I pi over 2 times r. So this is not 1 anymore. If it was 1, then it was a circular polarized, right? And then so A e to the power I phi x. So r is not 1. R is not 1. So you can see that this, when we plug in there an electric field, what the electric field looks like. So electric field at z t, and so for this it will be x hat, so real part of x hat, and this is common, so I don't include that. This one is just, I write down in this solid vector here, and y hat times r e to the power I pi over 2, which can same as I, this is equal to I if you wanted to be a little bit compact. And then you have amplitude A, and then you have e to the power I kz minus omega t plus phi x. that was the one that we writing with respect to, which is difference. Difference is what's important. If you're two waves, there's difference is what's important. Okay, so now if I do a real part with x hat, I just get the real part of that guy. So I get x hat a cosine kz minus omega t plus phi x. But for y hat, I get something more. I get I pi over 2 in here. So I get a r times a cosine kz minus omega t plus phi x plus pi over 2. So you can see now we have a situation in which this is the ex, and this is the y component ey. So if I plot, so this is like this axis will be along the ex and along the ey, and so we're going to plot not along x and y but along the ex and ey. We're going to call it the E field. So this is the E field, and of course this point to the x-axis, this point to the y-axis. Okay, if you look at this thing is actually minus sine theta, and theta equals to kz minus omega t over phi x. So it's like that. So if you look at ex, let me erase this because this is a very important point I'm going to make regarding this, how to deal with this. Okay, so I clean it up, and to show that this would be the x component. So like any vector, it has x component, but this depends on what place I'm and what time it is there, and this is the y component, and the y component will be this whole thing with a minus sign there. So y component, and notice that this is ex at any place and time is a cosine some theta, and theta stands for this stuff, and e y z of t, and this is the zt. This zt is inside there, and this is b minus sine theta zt. So you can see that ex, not E0, but the x component of the electric field over a. So bring a on this side and bring b on this side. Then if you square that and square that, that becomes 1 square plus ey over b square equals 1. And this is if I look at in the ex ey space. Okay, we're not looking at x and y space, we're looking at electric field space. In order to see the direction of the electric field, there's a here and there's a b here, and it is a, and this is where the x direction is, and this the y direction is. So this is a electric field, and it's because of this being a minus, it's gonna go around in this direction. So what we see, if I have pi over 2, and if we have these guys are just off by pi over 2, we end up going counterclockwise, okay, and aligned with the axis. So this ellipse is aligned with the axis. Ellipse axes are aligned with x and y axis. And so you can say this guy is A, this much is B, and you can totally study from here, from A and B. You can say, hey, where the focus of this ellipse is. There will be two foci, F1 and F2, right? And you can totally study every property of ellipse from given the ellipse equation in here. So this was a vector which was 1 here and some r e to the power I pi over 2. So that was the ellipse. This corresponds to this kind of elliptic behavior in the x and y directions. Okay. Now a more general will be not even have this, just completely generic. What would I get in that case? In that case, what you're going to get is if this is the x-axis and this is the y-axis, then the ellipse may be pointed in another direction. Okay, and there may be the x-axis is this way, y-axis is that way, but this is the ex-axis and this is the ey-axis. So and we can just say primes. It may not be the ex and ey, so the ex will still be this way, so it's in a different direction, so we can say y prime. So this aligned with a different x xy than the otherwise. And the question is, how do I see that? Okay, can this analysis let me see that and be able to find how it will be oriented? What kind of values do I need in here in order for that to happen? Okay, and I will say to you that what you need is not pi over 2, because this is already different. So this will be some delta, and delta is not pi over 2. Okay, and this angle, say, is alpha, and this alpha will depend on how much difference is in the phase between the wave that's going parallel to x-axis and the wave that's parallel to y-axis. Let's see that, okay, in a real calculation. Okay, so we are new drawing I did. So there are two components of electric field waves. One is in the xz plane, and we're not drawing the magnetic field. So the second one looks like a magnetic field, but it is also electric field, but it's in the yz plane. And the net electric field may be, if I'm at this plane, may look like that. That may be the net electric field wave. And so, because they're vector sum of these two waves, and writing the vector notation within column, using column just for organizational purposes, and let's denote this by delta y, because I want to keep track of this y with respect to x, because otherwise you're going to have a negative sign here, right? And to write more compactly, let's call this guy A, give this guy another name B for the sake of calculation, and later on you can just put wherever you saw A, you can put E0x, B, you can say E0y, just for the sake of calculation. So using this in here, what's going to be, it's going to be the same thing as we had written. It's really no big deal. Is E0 is going to be A cosine. So this way I can take this guy out, and then that's going to be, I just leave A0x here, is I phi x, and so this will be E0y e to the power I delta y. So it's going to be cosine kz minus omega t plus phi x. So that's just going to be something like that. But the y hat will be b cosine kz minus omega t plus phi x plus delta y, right? Plus delta y. So that's the total electric field. And so Ex is this, and let's call this theta. So this is theta as before. And theta is a function of z and t, as obvious here. So we have, and we're going to look into is originally my x and y compressed there, and then we're going to see how where the ellipse is here. Okay, so ellipse will be in Ex, this Ex of z and t is equal to a cosine theta. Ey of z and t is equal to b cosine theta plus delta y. And I need to get rid of get some kind of both cosine square plus sine square kind of deal here, right? So this would be b cosine theta cosine delta y plus actually minus b sine of this, I'm using big theta, sine of delta y. Okay, so you can see cosine theta I can plug in here, or Ex over a. So this is b. I just not gonna write that anymore that much. Just assume that we're dealing with the whole Ex over a cosine delta y. So this looks cool, but this guy's going to be square root if I do that. So minus b is square root of 1 minus Ex square over a square, and this whole thing sine delta y. So I need to get this square root out of the way. So I'll just say Ey and bring this guy on the other side minus, and then this equal to that. And maybe we can square this both sides. So we get a Ey square plus b square a square Ex square cosine square delta y, and there's a cross term minus 2 Ey b Ex over a cosine delta y. So this is the cross term, and that's equal to, on the other side is b square 1 minus Ex square over a square sine square delta y. Okay, let's multiply by, maybe divide by b square way worse. Okay, let's divide by b square. So this is 1. This becomes by square, b square, and this becomes b. So it's like Ex over a and Ey over b kind of going nicely. Okay, and so this goes away. Okay, so now we have a situation on the right side is sine square delta y minus Ex square over a square sine square delta y. Now you can see that this thing will match up with this and simplify. And let me erase something, come back to it. Okay, so this thing should look like this with that will make it Ex square over a square. Okay, a square was, remember, a was E0, x is a. just a constant, and E0y equals to B. Okay, so this is and the cross term is 2 E0x E0y. I mean this EX over A, EY over B, and you have a cosine delta y. Okay, and let me erase this and write over like this way. Okay, so write like this, and this other one will be EY square over B square, and bring the sine square delta y on the other side. So this is like a quadratic expression, right? Okay, so we have these coordinates, right? We have x and y coordinates, and with respect to that, if the electric field is this is my net electric field. You have this x component and this y component, and there's a mixed term here of Ex and Ey. What we want is rotate the coordinate system to find out where there's no mixed term. So we want want alpha such that when I rotate by alpha, this new coordinate system, I take components in that, this thing is actually not there. We want Ex prime something not A, let's call A prime square, plus Ey prime B prime square equal to 1, right? For a standard, let's call it A little p and little p prime square, because we'll have to absorb this guy, right? And so the ellipse will be like this, and so we want this alpha. The rotation of coordinate will take place like so. X equals to x prime cosine alpha minus y prime sine alpha, and y will be y prime sine alpha plus x prime sine alpha plus y prime cosine alpha. So it's going to be like this, right? And Ex, these guys will transform exactly like this. So whether you do it vector r, which is this is for the vector r, and the vector E will be exactly the same way. Ex will be written as Ex prime cosine alpha minus Ey prime sine alpha, and Ey will be Ey prime Ex prime sine alpha plus Ey prime cosine alpha. It's going to be written like that. And when you substitute in there, you're going to generate a whole bunch of terms, right? So you're going to just generate so suppose this thing is A, just call it little a, same as the axis, Ex square, let's call this little b, okay, I'm going to do it like Ax Ey plus little c, this will be little c, Ey square, and then let's call it plus d. Well, would it be d Ex, which is d equal to 0 here, so little e, this is equal to 0, not Euler thing, Ey plus f, which is this stuff is f equal to 0. So that's the case here. These guys are missing. This is a general quadratic expression. So when you rotate, you're gonna create, if you plug this in here, you're gonna create a prime ex prime square plus b prime ex prime ey prime plus c prime ey prime square plus d prime ex plus e prime ey prime plus f prime. They will be the same, right? F prime will be the same. None of them is inhomogeneous, not going to get created. So we want, after you express that, we want this to be 0. Well, what is that? I'm not going to do it. You do it out, and then you will find that when you do that, that gives you the necessary condition. So that's the angle we're looking for. That's the angle we're looking for. But we get twice the angle equal little b over a minus c. So in our case, little b is this whole thing. So minus 2 cosine delta y whole thing over AB, and a minus c, this is little a, this little a, and this little c, 1 over a square minus 1 over b square. So when you simplify it, I get this equal to b square minus a square, is cancelling the minus sign, gives me a square minus b square, and over there kills one of those. So 2ab cosine delta y. So this is equal to tangent to alpha. So that's the answer. That's how much you have to rotate. When you rotate, you get the angle. So this actually gives me the angle that the new ellipse is. It's either going this way or going that way, and that you have to figure out by actually looking at the phase of the cosine and sine, x and y components, how they're varying. Okay, so this is very interesting, that we can actually get out from this and this. We process the way I did. You can get the angle by which you have to rotate, and you get the direction in which the ellipse is pointed with respect to the original xy direction. There are other ways of doing this, but I think this is much more direct and makes more sense to me. I leave some exercise for you to do. There's like rotation on the coordinate to get from here to there, and how to get this condition. And also I leave exercise for you to find out, is it going to go this way or this way. Of course, that's going to depend on these phases that you have to choose. Suppose you choose delta y equals to pi over 4. What happens? Okay, so you can just play around with this example. And this is a long video but very instructive. So let me see what kind of things we learned. We learned how to deal with the complex numbers, how to actually complexify cosines and sines, to work with linear operations involving waves. It's a very useful trick. Okay, and so next one, we'll be able to just use complexification without worrying about it, because it's a good thing to have mastered it. Okay, all right. If you like this kind of video, I kind of appreciate if you hit the like button so that it gets more distributed. You might want to subscribe if you want more of my channel delivered to you or notified to you. I also have a website that you may want to check out. I think I'm gonna go out and do more upgrading on my website in the coming months. Okay, take care. Bye.